Hello and welcome. I'm Mohammad Afzal Shadab, a PhD candidate at the University of Texas at Austin, guided by Dr. Mark Hesse. Today, I'll talk about our research on fluid infiltration in unsaturated porous medium with the development of a saturated region. Let's first begin with an introduction to infiltration in hydrology. Infiltration is the process of entry of surface water in the soil to become soil moisture and its subsequent vertical motion through the Vadose zone. Its applications are aquifer recharge, pollutant transport, and agricultural water supply. There are three cases of rainfall infiltration. First is the case of light rainfall, where ponding typically doesn't occur. The second case is of excessive rainfall, where the ponding occurs almost instantaneously, depending on the capillary suction effects. Third case lies in between these two extremes, and here ponding occurs at a later stage due to reduction in porosity with depth. Interestingly, this third case is not investigated in detail, and moreover, typical models in hydrology assume single or double layered soils. And we know that soils can have arbitrary profiles with depth. We are interested in ponding time and the estimate of runoff. So hydrologists do experiments and moreover simulations using Richard's equation, which neglect the air resistance. Let's look into the modeling of this infiltration process. This infiltration can be considered as a two-phase flow of air and water in porous and rigid soil. It is modeled using Richard's equation because gas or air responds essentially instantaneously to dynamics of water. But unfortunately, in Richard's equation, there is a capillary pressure derivative term which blows up when the medium is about to fully saturate, or the water saturation goes to its maximum value, 1 minus residual gas saturation. In this particular limit, we are supposed to solve full two-phase equations. Now, if you look at the plot on the right, in this figure, the porosity is reducing with depth due to overburden. And if there is rainfall, the water infiltrates in this low textured soil, such as sand, where capillary effects are negligible. So the dynamics is gravity dominated, or the partial differential equation governing this model is hyperbolic. Due to constricted area, as the porosity reduces, you can have saturated regions forming in the domain. And in these saturated regions, full two-phase equations give rise to an elliptic partial differential equation. And our job is to integrate this saturated region into an otherwise unsaturated domain. And for that, let's look into the governing equation, which is nothing but the mass balance. Here, we are looking at the mass balance of water. So the first term is time derivative of the volume fraction of water or soil moisture content. So here phi is the porosity, SW is the water saturation, plus the divergence of the flux has to be equal to 0 since mass is conserved. The flux is a function of saturation and porosity, and in the unsaturated case, it is equal to unsaturated hydraulic conductivity, whereas in saturated case, it comes out to be a constant QS, and we do not know what that is. So to know the value of QS, let's look further into this saturated region. Inside the saturated region, the residual gas phase is immobile, and moreover, the boundary conditions at these unsaturated and saturated interface is water and gas pressure equivalence, which means that pressure of water is equal to the pressure of gas, which is equal to 0. And from that, we can calculate this value of flux in the saturated region, which comes out to be spatially invariant. And its value comes out to be a harmonic mean type formula, where you have water density, acceleration due to gravity, endpoint relative permeability of water divided by the dynamic viscosity of water, multiplied with harmonic mean type relation for absolute permeability. And that is equal to the harmonic mean type relation for hydraulic conductivity. Now, using this spatially invariant flux, we can find how fast these saturated, unsaturated interfaces are moving using a tool from the hyperbolic analysis called Rankine-Huguenot jump condition, which says that the front velocity is equal to jump in the fluxes divided by the jump in the soil moisture content or water volume fraction around a shock wave. And now using these two informations, we can now delve more into how the infiltration behaves with respect to changing in porosity with depth. And for that, I'll show you 3 cases, starting with the porosity with the single layered profile, where porosity stays the same inside the whole domain. And as you can see, on y-axis, there is a dimensionless depth, and on x-axis, there was volume fraction. And you can see that there is a single front, which moves with constant velocity, and it propagates downwards, and behind the shock, the region is still unsaturated. But what happens when the medium has a porosity reduction with depth? In that particular case, something interesting happens. And as you can see, due to downward reduction in porosity, the initial front bifurcated into 2 fronts. One moved upward, one moved downwards, and the region is fully saturated. This happens because the lower layer is unable to accommodate the rainfall flux coming from the top layer. This also happens if there is a continuous reduction in porosity with depth. And this is the case for exponential porosity variation. We have also studied the power law porosity variation and found analytical and semi-analytical result for ponding and runoff, which are not shown in this talk in interest of time. Here, we'll only focus on the 2-layered profile, and we want to talk about the formation of the saturated region. Here, these are the time sequence snapshots of the video shown on the previous slide. We can divide the dynamics into 3 stages. In stage 1, there is an initial front which moves downwards. And in stage 2, that front bifurcates into 2 fronts. One moves upwards and one moves downwards, which are bounding a saturated region. And the 3rd stage is when the upward moving upper shock reaches to the surface. And when it reaches to the surface, it disgorges the rainfall flow, and it causes a drop in the infiltration rate. So that amounts to the runoff or ponding. So we have seen in our research that the velocity of these fronts are constant. And moreover, the flux in the saturated region is also constant before ponding occurs. And we validated these analytical results with the numerical results. And here are the corresponding water saturation profiles for the same test shown on the previous slide. Here, the solid red line are the numerical results coming from our novel hyperbolic elliptic PDE solver based on domain partitioning. Dashed black line corresponds to the analytical result. And as you can see, we agree fairly well in all 3 stages. And we validated this 2-layered profile with Hydrous as well, where it validated quite nicely, but we haven't shown it here in interest of time. But now let's talk about something important, which is the infiltration rate. What happens when there is choking as well as ponding? What happens to the infiltration rate? To reiterate, infiltration rate is the water flux at the surface, and its maximum value would be saturated hydraulic conductivity, FC. So we are looking at its ratio and its evolution with time. And initially, it was equal to the rainfall rate, but even when saturated region formed, the infiltration rate did not drop because the surface is still unaware of what is happening at a certain depth. But when the backfilling shock reaches to the top, it disgorges the rainfall, and there is a drastic reduction in the infiltration rate, and that amounts to the runoff at ponding. And that reduction in infiltration rate is further increased with time, because we are percolating more and more into the lower layer, and it asymptotes nicely to the saturated hydraulic conductivity of the lower layer. And next is to use these infiltration rate and try and construct the analytical results. And I'd like to give you a flavor of that. So here's the water flux profile for the upper layer with high conductivity shown in this blue curve. And on x-axis, you have water saturation. For water saturation equals 1, we are in elliptic, fully saturated region. Here you can see the two dots. One is the rainfall rate and the other is the flux of the dry soil. And you connect these two by a straight line in this convex function. So the slope of this line corresponds to the speed of the front. So initially there is one front which moves downwards, but in the second stage, instead of directly dropping to the flux of this dry layer, it first goes to the fully saturated region and the value of dimensionless flux. And from there, it drops to the dry region. And it turns out that the slope of the first shock is negative, which means that the shock speed is negative and the shock moves opposite to the direction of gravity, that is in upwards direction. And after ponding, we find that the rainfall rate is not useful. And what is useful is what the soil can accommodate into it. And that is equal to the dimensionless saturated flux. And you have an stationary upper shock here sitting at the top. And then there is a lower shock which connects to the dry soil. At this point, gradually moves to the saturated hydraulic conductivity of the lower layer. Now let's look into how each fluid particle is moving. How about that? So this is a space-time diagram of particle paths. On x-axis, you have dimensionless depth, and on y-axis, you have dimensionless time. Think about a fluid drop which enters the domain at some time t greater than 0. It traverses these sky blue lines, which are the particle trajectories. And the slope of these lines is equal to dt over dx, which is the inverse of the velocity, which means that if the trajectories are horizontal, it means infinite velocity, and trajectories are vertical, means zero velocity. So here you move with constant velocity until you cross the upper shock, upward moving shock. And since the flux in the saturated region is lower, so the shock speeds or the particle speeds reduce and the slope increases. But for the same volumetric flux, when we enter the lower porosity region, the velocity has to increase to accommodate for that. And once we are in third stage, these trajectories become curved because the velocity is now changing with time as the infiltration rate is changing with time. The last thing I want to show is the effect of rainfall rate and lower layer porosity on the dimensionless infiltration rates. And here you can see that we fix the porosity of upper and lower layer, and we are trying to change the dimensionless rainfall rate from 0.2 to 0.9. And we found that for the maximum rainfall, we saw fastest ponding happening and shortest time of ponding. And the runoff was maximum for the maximum rainfall, since every shock moves faster and the amount of water is a lot. So this happens. The other case is when we fix the rainfall rate and we fix the upper layer porosity. And now we change the lower layer porosity from 1% to 40%. Here, we found that the ponding occurs most rapidly for the case of 1% lower layer porosity. And moreover, the runoff was maximum. And the reason being that 1% porous layer acts almost like a wall where very little fluid percolates through it. And most of it just accumulates rapidly on top of it. So backfilling shock is much faster. And that's why ponding occurs rapidly and the runoff is so large. And with that, I'd like to conclude my presentation. In this work, we developed a general framework for solving hyperbolic Richards equation with saturated region. This theory is applicable to low textured soil with negligible capillary suction effects We investigated the case of transitional rainfall, which led to choking and ponding. We further investigated the two-layered profile, investigated that shock speeds and flux came out to be constant before ponding. We validated the analytical results and analyzed the evolution of water particle parts. This theory can be extended to soil with initial saturation and arbitrary porosity variations as well. Now, for me, the next step is to also consider energy balance and take a step further and investigate infiltration in cold firn. And for that, check out my poster on analytical solutions for melt percolation in ice masses and a pathway to ice lens formation. With that, I'd like to thank you for listening. Have a nice day.